Let's get steppy here on Nick Does Maths. Today we have a fantastic question from the STEP library. But before we do this, please check out the link in the description for access to our My Headspace cram courses running into all throughout the exams. The night before your exam, you get a 3 or 5 hour revision session with our expert teachers getting you ready for the next day. All the information in the link below. Let's do this. Let's write down some general terms of these expansions. We're then probably going to use them, STEP tends to do that, to figure out these sums. And then we're going to do something which is the related but a little bit more difficult. Right, well, there's going to be some erasing here, right? I'm going to just populate what I can. So 1 minus x to the minus 1, well, 1 minus x to the minus 1. You can use the binomial expansion formula that you probably have somewhere from your A-level textbook. You can use Maclaurin series, however you want to view this, right? I'm just going to go straight for that sort of general binomial expansion formula. And this one I just know. Why? Because it's a cool expansion, because it's 1 plus x squared plus dot, 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 dot. Now, looking at that, what is the general term of that? Well, the general term, I'm going to write it in summation notation. It is just x to the n. Fairsies. Now what's kind of sneaky here, right, what's kind of sneaky is I could differentiate that to get this result. But I'm going to do it from scratch, but you could also play around with differentiation. And we'll do it 2 ways, and then we'll do the minus 3 as well. We do just need to be very, very careful about first terms. All right, but fundamentally, right, x cubed plus, do you know what, I'll put in another one. So if we differentiate it, this is minus 1 minus x to the minus 2 plus, we pick up a minus from there and a minus from there. So 1 minus x to the minus 2 is 1 plus 2x plus 3x squared plus 4x cubed plus dot, 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 dot. Ha ha ha! Take that. Or you could use the binomial formula. You will get these out as well, but this actually tidies it all up for me. So in fact, having said I'll do both, I'm just going to quote differentiation. And that will be, now, ooh, we do have to a little bit be careful. So I'm going to call this n plus 1 x to the n. X to the 0, we get a factor of 1. X to the 1, we get a factor of 2. X squared, we get a 3, and so on, so forth. Now, you will notice that that's not a direct differentiation, but really it's so I can start from n is 0. All right, it's so I can start from n is 0. If you want to start at n is 1, you would just differentiate this. All right? So let me actually show you that in action. Right? Say this is my f of x. If I did differentiate that, I would get, and that's not a problem. The issue is, of course, when n is 0, when n is 0, there is no term. So part of that is completely not needed. And we could go from there. And all we're doing is we are shifting the relevant numbers here. All right, so if I start here with n is 1, I'll get 1x to the 0. If I start here with n is 0, I get 1x to the 0. They are équivalents. Comme un croissant. Croissant. Right. I can differentiate this again because I'm cool like that. The 1 disappears, so I'm left with 2. And I'm going to write it this way, 3 times 2x plus 4 times 3x squared. In fact, I would get 5 times 4x cubed plus dot, 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 dot. Now, I do have to divide all of this by 2, but I'll do that in a second. Now, these terms here, how are they? Well, so let's divide by 2. We get the 1/2. We get the sum, n is 0 to infinity, something to do with x to the n. Now, what goes in front of it? Well, again, n plus 1, n plus 2. We're going to need a bit more space here. All All right? Now again, you could differentiate that. You could differentiate that twice. You will probably be out here with n minus 1, and n minus 2. But you will be starting at n is 2 because the first two terms would give you 0. You could try it out, right? But that is my general term. So differentiating. Also, you could just go through your formula for the general term of a binomial expansion. You can Maclaurin series, you will get this out as well. But once you got one of them, you are absolutely free to differentiate to get one to the other to the next. Why not? Okay, that's part one. That's part one. Now, how are we going to use that for part two? Well, first of all, let's remember that all of this is only valid for mod x is less than 1 because it has to converge. And now let's look at this. Let's look at it. Right. So in fact, looking at this, we probably, look, we're starting at 1, we're starting at 0, but we'll deal with that in a second. Now we look at that, 2 to the minus n, x to the n. What that tells me really is that we're going to use x's 2 to the minus 1, also known as a half to you and me. All right. So let's plug that in. That is 1 minus a half to the minus 2 is equal to the sum, n is 0 to infinity, of n plus 1, 2 to the minus n. Now, I want both of those to be the same. All right. So what we're going to do is, actually, we're going to take the version where we're going to go from 1 to infinity, n 2 to the minus n plus 1, n minus 1. Because that is the sum, n is 1 to infinity, of not enough board space. What we'll do is we'll do our derivation, I'll plop it over here, and then we'll go from there. That is the sum. Is that correct? If I put 0, my first term is 1. Yes. And if I put in 0, the first power should be 0. If I put 1, the first power should be 0, 0, 1, 0. Yes, we're OK. Because that is n, 2 to the minus n, times 2. Now let's deal with this side. 1 minus a half is 2. 1 minus a half is 2. 1 minus a half is a half. Silly boy. A half to the power of minus 2 is 4. So what that gets me is divide both sides by 2. And we will get our result, which I will put up here. The sum from n to 2 minus n, 1 to infinity, is equal to 2. Excellent. All right. Now, don't know what's going on there. We're now going to play with this one, as you might be able to imagine. Let's take this guy for a little spin. 1 minus x to the minus 3 is 1 half. N is 0 to infinity. We might have to play a little bit with the indexing again, but we'll play with that in a second. But the point is if I expand this and split it up, that is n squared plus 2n plus 1 x to the n, which is 1 half of n squared x to the n, plus a half and a 2, from 0 to infinity, plus 1 half the sum of x to the n from 0 to infinity. Okay. This is our key here. Now what you'll probably notice is the 0th term here does nothing for me. All right, which is why I'm going to go to 1 here. That's absolutely fine. Not a problem. So I don't even think we have to muck about too much. And funnily enough, we are also going to plug in x is a half. So I end up with 1/2 to the power of minus 3 is 1/2. And I'm just going to nip out that 0th term because it's just 0, so I don't need it. Again, here the 0th term is not needed, but it's just the sum of nx to the n, n2 to the minus n. That is going to be n2 to the minus n, which you already figured out is there, so that's a +2, so that's nice. Plus 1/2 the sum of 2 to the minus n. Now, if we do that here, if we plug a half into here, we will get 2. Now that there is 8. 1/2 to the minus 3 is 8. Minus 4. Aha! But that's 2, so that's a 1. That almost went catastrophically. I forgot about that 1/2. Never forget the 1/2. 8 minus 3 is 5. So that will tell me that this is 10, apparently. Do you know what? I would check it on the old calculator. If I had one, never mind. Never mind. Does the 991 do summation for me? It will try. It will try. So let's see if we can get a little check on this. So what are we doing? We are doing n squared 2 to the minus n. Where's the x button? X squared times 2 to the power of minus x. That's useful. Is that the same button? Tune in to see Nick plug stuff into a calculator. N is going from 1 up to 100. Or did I break it? Oh, that's telling me 6. Oh, that's telling me 6. Why is it telling me 6? Why is it telling me 6? Oh no. Why is it telling me 6? Yeah. How many of you have been screaming at this, that that's a 3n in there? Oh, how many have been screaming that that's a 3n? So that's 3 over 2. Oh. Still no good, but we'll get there. And that's a 2. Oh my Lord. Oh my Lord. There you go. There we go. Tell you what, nice example of why it's worth checking your work numerically. If you have the right tools, even the old little class whizzes, they can do some summation for you. Just put in a big number, and that let me check my answer. And look at that, how easily I thought I expanded that quickly. I was an absolute silly sausage, let's go for, and I missed out a bunch of those. So hopefully you picked up on that as I was going through it and you were wondering yourself, what has he done? He did a mistake. Right, so, lovely. Own it, we move on. He says as he erases all proof of this mistake. Okay. Part 3. Let's do something with this. 1 minus x to the minus half. I'm going to have to do this like a grown-up because I can't differentiate this at all to get to there. So I'm going to have to. So let's get a few terms out. 1 minus x to the minus a half is 1 plus minus a half times minus x plus minus a half minus 3 over 2 minus x squared over 2 factorial. I'm going to put a couple more terms here. Do I have the space? No, so I'm going to have to go underneath. Plus minus a half minus 3 over 2 minus 5 over 2 minus x cubed over 3 factorial. And we'll do one more. Minus a half minus 3 over 2 minus 5 over 2 minus 7 over 2 Right. Now the important thing here is that the minuses always cancel out minus, 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 all positive. So that's a good start. Now what bits have we got here? So x to the n. Well, x to the n is there, so that's cool. Now we sort of have a 2 to the n. We sort of do. We sort of do. We've got our n factorial, and then it's all about this 2n factorial. Now let's have a little think about what we've got. So by and large, the numbers I'm really interested in here are these numerators, right? The rest of it does what I want it to do, right? I've got an x to the n. I've got an n factorial, and I've got a 2 to the n. And the last thing I want to look at are these. Well, our hint is in what the question's suggesting. They're suggesting, look at 2n factorial. Okay. So let's say here, remember that is n is 1, that's n is 2. Let's look at n is 2. If I do 2n factorial, that is 4 times 3 times 2 times 1. Well, I only want 3 times 1. So let's divide it by 4 times 2. But 4 times 2, right, what is 4 times 2? So on the top here, I do have 2n factorial, so that's nice. Now, what's 4 times 2? Well, 4 times 2 is 2 squared times 2 times 1. Why 2 squared? I've pulled a 2 out from there, and I've pulled a 2 out from there. But that's just n factorial. So that is 2n factorial over 2 to the n factorial. Will that work with n is 3, I wonder? So I want 6 times 5 times 4 times 3 times 2 times 1. That's my 2n factorial. I want to get rid of the 6 times 4 times 2. But again, if you pull a 2 out from each of those, that's 2 cubed. Pull a 2 from there, from there, from there. You're left with 3 times 2 times 1, which is my n factorial. So that's that term there. So all of that to say that this numerator that I've got there, the 1 times 3, the 1 times 3 times 5, 1 times 3 times 5 times 7, that is in fact 2n factorial over 2 to the n factorial. And that gives us what we wanted. All right, n factorial squared, bosh bosh, 2 to the 2n, bosh, bosh. So that's kind of cool. That's kind of cool. And this is from, now does that work for n is 0? 2 to the 0 is 1. 0 factorial is 1. Trust me, I've tested it. Not even sure what that means. X to the 0 is 1. So that does work out. We do get 1 for our first term. And how about 1 factorial, 2 factorial, 2, yeah, that works out. Okay, well let's have a look here. What does that mean for this sum? Well, quite obviously, I end up, the only thing that's missing, is that 3 to the n. So we are just plugging in x is a third. If we get x is a third, I get square root of 3 over 2. 1 minus a third is 2/3. Reciprocate, take a square root, is the sum from n to infinity of 2n factorial over n factorial squared, 2 to the 2n, 3 to the n. Isn't that a result we all wanted to know about? Now, we might be able to do something funky. Do you remember how we got from there to get the n involved? Well, look, we've got an n involved. And also, we're starting at 1. Let's differentiate this. 1/2, 1 minus x to the minus 3 over 2 is equal to the sum, 1 to infinity, of n, x to the n minus 1. Now we are going to have to deal with that in some way, shape or form in a second, times all the rest of the governs. But really what we are going to do is take a little bit of space up here. Again, just eating up the whiteboard, eating up the square meterage. We're going to plug in x is a third again. 1/2, 2/3 to the minus 3 over 2. We might have to play around with that a little bit. Is equal to the sum, n is 1 to infinity. Why 1 to infinity? Well, the 0th term won't do anything. 3 to the 1 minus n, I do believe that becomes, times 2n factorial over 2 to the 2n, n factorial squared. And basically, I can just pull that 3 to the 1 out front. All right, I'm just going to pull that 3 to the 1 out front. 1/2, let's flip this, 3 over 2 to the 3 over 2. Yeah. Not entirely sure where this is going for me on that side. That is 3 times the sum that I want. Bring that in. Can we tidy that up a bit? I mean, probably. I'm actually just going to, that is root 3 over 2 times 3 times root 2. All right. Now, does that cancel anything nice? I mean, sure. It is what it is, right? 1/4 square root 3/2. Maybe take the one, maybe take that into the square root. I just don't think it does anything particularly nice. No, doesn't do anything particularly nice. So I'm going to stick with this. And there we have it. A fun little bit of summation. There we go. Get some really funky results out of this. The real skill being tested here is your ability to use summation notation all the way through and to look at this idea of a general term. That is really what's being tested of you here and what the examiners were looking for in this particular step question. Bosh. If you're still with me, well done. I'm Nick. Don't forget to like, subscribe, hit the bell for notifications so that you don't miss the next one of these, and I will see you on the flip side.